Well, I'm going to start by passing Ernst Haeckel's book around. I don't know how many people are familiar with it, but there's great pictures of things in nature that have sort of a random geodesic structure to them, and it's just a great book that you should take a flip through it a little bit. Let's say my favorite Bucky statement is dare to be naive, and I'm just naive enough to think that there's a better way to make a dome, and so I was looking for it, and I really didn't care for spherical trigonometry, and I didn't care for calculus, and I think Bucky said, in order for you to have calculus, you got to have 360 degrees around a point, which cannot be true for a polyhedron or a sphere. There's got to be an angular deficit. So it sort of starts off from a wrong premise somehow, I guess. And so I told you this morning I started playing with paper plates at one point, and I got the idea that you could consider a vertex as a unit rather than as the junction of two edges or the corner of a face. I started to look at vertexes as a cone, basically. A cone is at minimum a tetrahedron, so a vertex at minimum is a tetrahedron. It could be hexagonal pyramid, it could be something else, but a cone pretty much covers what a vertex is, and that's compound curvature. So from the paper plates, I considered using a cone, and that's what I did. And I took circles of paper and very carefully sliced out 2 degrees on this particular model and taped it back together so that I have this concave, convex vertex element. And Bucky liked the word, started using the word vertexian. I guess that didn't really catch on anywhere, but that's really, I think it's really what we have to do is like consider the vertex as the most important part, you might say, of a polyhedron. And the one thing about a vertex that you can always say is that it has some kind of angular deficit. It can't be flat. So I know that there's 720 degrees of curvature in a polyhedron, and so if you divide that by the number of vertexes, n, no matter if it's 5 vertexes or 7 vertexes, it doesn't matter, you can get an alpha, which is the angular deficit of that vertex. So that's what I did, and I didn't pay any attention to the distance between the vertexes, or really the shape of the faces, and just assembled it, and I started making these very spherical-looking polyhedrons with just that one simple fact. And I started looking into it further and further. Talking about naive, I am naive enough to think that this might be important, so I did apply for a patent. It seems, one of the reasons I came here was because this seems so trivial that it seems like, well, you must be missing something, Dick. It's just like too simple to to work, but it does work, and I'm still in, huh?
Simple is good.
I didn't, I wanted people to get inside, and that's really where Bucky started a long time ago with his 4D. He wanted to mass produce shelter. So I always had that in the back of my mind, and I thought simpler was better. And so this boils down to a single vertex element that can be repeated more or less arbitrarily. There has to be overlap. You don't want a hole there, so it's not completely arbitrary, but it's more or less arbitrary. And you're always, of course, going to get 5 pentagons and the rest hexagons. 12, I'm sorry, yeah, 12 pentagons, and so that always comes out without even looking for it. If you just start putting these together, you can go back and you'll find them someplace. They have to be there. Also this turns out to be related to an old problem, which is endpoints on a sphere, which I didn't know anything about at the time, but there's a whole bunch of people out there that have different ways of distributing, say, 100 electrons on the surface of a sphere, so that they're all repelling one another, and they're as far apart from each other as they can possibly be. And I don't think anyone's really come up with a very good way to do that. There's many ways to do that, but I don't think there's any really simple way to do that. But this is one of them. And how it works, the simplest way that it works to conceptualize it is if each one of these circles is a vertex. It can either be an acute cone or, well, these are obtuse cones, but it's just as good to have an acute cone whose apex is the center of the sphere. So if you look at these as vertexes, and I just picked a certain size glass to use as my circle, and I started at the top, and I just started doing a spiral. And each vertex is tangent to the last one. So it goes here, 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 all the way around in a spiral. And I'm not trying to fit them in closer to one another. It's like a string of beads, basically. And so if I want to add one more vertex to this structure, the whole thing rotates. The whole spiral has to expand a little bit. And you can do that as much as you want. These lines, these rows, just pass by each other. And so it's pretty easy to distribute endpoints on a sphere in that manner. I'm sure there's a million ways to do it, but that's an easy way to do it. And so that's that. You can also take well, I use these little drink umbrellas as cones, but you can also have a bowed either cross member or a triangle, and you can put a cable, a tension member around the outside to give it that curvature. And it'll have some alpha, some angular deficit, and then you can attach those structures, which are, I guess they're little tensegrity structures, and you can overlap those and form a sphere that way too. So there's actually several ways that this manifests itself. This is simply a collection of great circle arcs, randomly assembled. I just started cutting arcs out of this paper, and when you fold it, the fold line becomes a radial line. And any place you attach two great circles, you get they attach along a radial line. So it doesn't matter where the vertexes end up, because each one of these is a spherical triangle out of necessity, out of construction. And so that's another way that this idea can manifest itself. I haven't actually related alpha to the central angle yet, but I think that's not too hard. I just have to play with the algebra a little bit more. Joe has his models over there which have equal central angles, and so there is a way to figure that out, but I haven't done that yet.
So you cut all the arcs so they have the same radius?
Yes, they all have the same.
How do you go about that?
Well, I just have an X-Acto knife on a circle cutter, yeah, and so I just fed in the construction paper, the poster board, and just made a slice, moved it down. You know, I arbitrarily, the thickness of this is totally arbitrary. You know, the thickness of the strut.
Use a compass to trace.
Well, the knife is the compass.
Oh.
The knife, it just you know, you don't have to use scissors or anything. It's a lot faster just to use a knife. So you make a cut, you slide it down, make a cut, and it could be plywood, it could be aluminum, it could be fiberglass, and it'll still work. This is the same thing, acute cones. These are actually paper cups with the bottoms cut out. They can all have the same perimeter, which will not give you same area triangles, but it doesn't matter, because the curvature keeps everything where it's supposed to be. And so I think, even though this isn't an octet truss, I think if you draw a line from the outer vertex here to the inner vertex here, and another one here, I think this is like a redundant octet truss. I'm pretty sure, but I don't know. I haven't actually seen the octahedrons, but I think the octahedron is from this corner here to this corner here are the two ends of it, and then
you can get a topologically. You can get a topological octet truss. It just won't be regular.
Okay, right.
You're only messing with the geometry.
Right.
The topology.
So, but structurally, it'll have the characteristics of an octet truss except there's going to be the longest strut is going to be the weakest one, obviously. But except for that weakest
you have
point.
Structure there, and you can relate it to an octet truss. After that, you just have to do analysis to see.
Okay. So, and here is the last one I'm going to show you. This is made out of these great circle arcs, just like this, except it's been pushed in so that it has three legs like that. But all the angle is still there, and then you can just connect them so that this great circle is continuous. And she comes out pretty good. You know, it's sort of organic the way you see those pictures in that book as it goes around. It's more, I get like egg shapes sometimes, and but you can distribute these things so that you do have equal area triangles if you want to. There's no reason why you can't place this vertex so that these two triangles are exactly the same as this one, And then once you get that, then you can put this vertex so that this triangle here is exactly the same size as that. So you can maintain equal area if you want, and you can also maintain equal perimeters if you want. Or you don't have to do either. So that's about it. It's simple, and I think I'm hoping that maybe a lot of people, homeowners, can start building geodesic domes in their backyards without any tables or without any knowledge of trigonometry, and I don't know. I sort of my
RanDomes, not geodesic domes. Yeah. These are your domes.
RanDomes, I'm calling RanDomes, right? RanDome geodesic structures.
They aren't geodesic. They're RanDomes.
They are geodesic as far as I'm concerned. I don't know why they wouldn't be.
I can answer that question, but I'll do it later. So. Geodesics means that the points of the triangular lattice, typically Fuller used the icosahedron. With his patent and most of the methods are good. Within the general face, you have 20 equilateral triangular faces. Within each face, as you all know here, you subdivide it into a regular triangular lattice with only the fact that the points within that lattice lie on a great circle arc makes it a geodesic dome. By doing what you're doing, you remove the restriction, the requirement that the points in the subdivided lattice lie on great circle arcs.
Well, a geodesic structure doesn't have to be a sphere as far as I'm concerned. It can be a saddle.
Yes, but then you have to talk about, do the points of any sequence of points lie on geodesic arcs?
Right.
And these aren't even restricted to that. That's actually good news.
Okay. Well,
I mean, if you're
it's awful. I mean, okay. Okay, so maybe
it may not be good news. But for the purpose of building simply and directly, it's very good news.
Okay.
So
Okay.
you've done
So,
a very good
well, it's awful close to a geodesic dome if it doesn't meet the technical definition, right?
Around here.
Okay.
Believe me, I'm not finding
Yeah.
fault.
Okay.
I'm supporting
Okay.
that you're building your domes. These are not geodesic domes. And they serve the same function as enclosures that geodesic domes do.
But I don't quite get that. But
Flower Days doesn't call his domes geodesic.
well, they're not because those are small circles.
Well,
Yours are too.
No, this is not a small circle at all. It's a great circle.
But the
And
sequence of the vertices don't lie on great circles.
doesn't matter. Doesn't matter.
That is the definition of a geodesic
That's-
dome.
No, I don't. Well,
Geodesic dome, if you project that triangle lattice onto a sphere, not all of those are going to line up.
Any sequence that comes from the straight line from the general icosahedral face, any sequence of points that's a straight line in that face project by definition to great circle arcs.
But
And
historically,
the struts are not great circles, they're chords.
they're chord.
So it's only the point set that lines up, that happens to land on a specific great circle arc that gives the meaning of the definition.
But the interesting thing,
It's just very picky, but it's accurate.
you're absolutely right.
I happen to know that. Thank you.
Yeah. So I'm confirming it.
Yeah.
well,
But historically, the term geodesic dome has now come to have a much broader meaning than it was even, no. I know the absolute mathematical meaning of geodesic is a geodesic arc is
Right.
the shortest distance.
Right.
On the curve. On
The
the
fact
curve.
that words degenerate into
Correct.
very loose usage, I have no,
Slang.
Walks like a
Well-
duck in the tuxedo.
But we live in a world where the world goes ahead in its own direction and decides where it's going to go rather than where somebody who's defined a definition ultimately defines it.
right,
And unfortunately, and I say unfortunately,
right.
even in Bucky's lifetime, he himself misused the word geodesic in describing his structures.
Well, if you want to go into marketing, you use it wherever you can sell it,
Yeah,
but in a group
so-
like this that's far more disciplined, I hope we can keep clear
Yeah.
that what's geodesic and what isn't, and
Well,
And you're absolutely correct, and
And
and not only that, but.
I totally support RanDomes.
okay.
Great.
This is,
Joe, given what you just said, what term do either of you, would you apply what, use for what you say?
He's coined his own term. I think it's fun. RanDome to rate it.
RanDome's fun.
It's fun.
Yeah, I
That
think
was
it's a
great.
great term too.
I hardly ever gave names to
But-
anything.
but-
I did.
I think it's great
I-
to have a clear definition.
Yeah.
I think it's good to
Have-
sense that there's a sociological thing that's gone on that has brought Dick to call these geodesic domes in that broader sense of the word. But speaking here, I can see a really good need to say, well, you know, in this particular group, it would be really nice if we were keeping different terms, you know, clear, so that when we're communicating with each other, we all know what we're talking about. I think that's the main thing is
Yeah, and that's part of the point that I'm trying to make, is the fact that from that Buckminster Fuller's, quote, first geodesic dome was the only one that was really a truly geodesic dome. But he continued to add an inventory of different methods and different algebras, I'm sorry, geometrical solutions to the topology. And that's an unlimited number. I mean, you can
I
place,
agree, yeah.
you can place the points on the surface of the sphere with an unlimited number of grids.
Right.
Triangulated.
Right.